The purpose of this semester was to design and build an autonomous rover that can complete certain objectives. The first objective was to have a user input a given distance in feet into a web server and have the rover travel that distance in a straight line. The second objective was to have the user input a given x and y distance in feet and have the rover travel that distance accurately. Both the first and second objective were graded competitively based on accuracy against all the other groups in the class. The third objective was the same as the second objective, only with obstacles blocking our path. The fourth objective was to have the rover autonomously find a cube that we designed. Our cube used infrared LEDs on the cube and an IR receiver on the rover. The final objective was to complete the fourth objective with obstacles on our path. The optional requirement was to track movement and plot any obstacles encountered by the rover onto the LCD screen of the ARM board, which is the main processor of our embedded system.
So I'm going to start with a quick overview of our data flow for this project. This is the ARM, our main processing unit. This handles all of the data that the rover collects and also sends out requests for data, and also, once done handling the data, it sends out motor commands to the rover. The ARM communicates over an I2C bus to this slave pick. This slave pick compiles all of the data that the rover collects via this XB wireless device. The XB wireless device is connected to the RX and TX pins of the 2680. The RX pin is where UART data is received, and the TX pin is where UART data is sent out. The PIC slave device communicates to its XB counterpart connected to the PIC 45J10. The 45J10 is our master I2C device. This device receives any writes via the XB and then sends them along our data path. The 45J10 also sends out data requests to our next PIC, which is then sent via UART to the XB to its counterpart on the PIC slave. This is our IR sensor and motor controls PIC. The motor controls end here and then are transmitted via the TX UART pin to our motor controller. Our IR sensors are connected to the GPIO pins, and that is where the IR sensors are read, and then the data is handled and the cardinal directions are sent via I2C back to the master PIC.
The motors are controlled through the Sabertooth motor controller. The motor controller has several different modes. However, we use simplified serial mode. A PIC board sends motor commands as 1-byte values through UART to the motor controller, which then powers the motors. In order to measure the distance traveled, we attach encoders to the motors. These encoders rotate with the motors and send multiple pulses for every rotation back to the PIC. This motor controller also supplies 5 volts and powers all the devices on the rover. The encoders are powered by 5 volts and send 0 to 5 volt pulses through their A and B wires. The A and B wires show which direction the encoders are turning. We decided to only use the A wire for both encoders since we know which way the rover is turning based on our motor commands. When an encoder pulse occurs, it generates an interrupt on the PIC 2680. This then increments a count and checks whether it has reached the appropriate count to complete its motor command. Once it has reached its destination, it will shut the motors off. We also inserted states into our encoder interrupts to calibrate our turns.
In order to complete the obstacle avoidance objective of our project, we chose to use and implement the ping ultrasonic sensor, which you can see here. The sensor has 3 lines: power, ground, and the data line. Power and ground are fairly self-explanatory. The data line is what actually operates the sensor, and this is wired to a GPIO pin of the PIC18F45J10. In order to pick up sensor readings, the data line must be driven high for a period of 5 microseconds. This acts as a start bit for the sensor. Upon receiving the start bit, the data line must be driven low for a period of 750 microseconds. Finally, the line is then driven as an input for the PIC, and the sensor will start driving the data line itself. The sensor will drive the line high to a signal when the sensor has emitted its ultrasonic pulse. Upon receiving the pulse, the sensor will drive the line low. During the time between when the sensor drives the line high and low, timer 0 of the PIC is counting. When the sensor is done operating, timer 0 is stopped and its value is read. This value corresponds to the pulse width of the sensor, which is then converted to distance in centimeters.
In order to find the cube, we implemented an IR emitter and receiver. The IR emitter uses a 555 timer circuit in order to pulse the LEDs at a 56 kHz frequency, as this is the only frequency that our receivers can decipher. The LED's voltage source is connected to an NPN transistor, whose gate is controlled by the 555 timer circuit. This pulses the LEDs at the proper frequency while also allowing the maximum amount of current to the LED, which maximizes their range. The IR receiver is a Vishay TSOP 341 IR receiver, which can detect any 56 kHz IR signal. We use these sensors in a directional array so that we can output the cardinal direction of the IR signal relative to the rover. Each receiver is hooked up to a GPIO port, or general purpose I/O pin, on the PIC 2680, which is a PIC processor we use to acquire sensor data.
When it came to mapping out the room, we decided that it would be advantageous for us to be able to see more than one point directly in front of our rover. In order to accomplish this task, we decided to mount our ultrasonic sensor on an HD analog servo, which hangs off the front of the body of the rover. This servo is controlled based on a pulse width modulator we designed based on timer interrupts. The pulses are sent out at a frequency of 50 Hz from the PIC 45J10 over the data line of the servo. Different pulse widths are applied based on the direction we want the servo to rotate. In order to collect the data we wanted, we set the servo to rotate on a 180-degree sweep about the front of the rover, which allows us to gather 12 points using the ultrasonic sensor. This populates a histogram. The histogram is filled with the distance from the rover of any obstacle in the scope of the sensor. When we detect an obstacle in a cell the rover is in immediate contact with, we mark it on the map so the navigation task can make a decision of where the rover should travel to next.
One of the most important parts of this project is successfully designating a goal for the rover to go to. The mapping task is in charge of setting the goal, and it sets it based on the current objective. The first objectives are very easy to set. You simply plot a point on the map with the goal relative to the rover. For example, in order to tell the rover to move 5 feet ahead, you simply find the rover on the initial map and plot a goal 5 cells ahead of it. For objectives 4 and 5, plotting the goal can be a bit more tricky. Because the rover has no idea where the cube initially is, the mapping task randomly plots a goal on the map. The mapping task will continue plotting random goals on the map until the IR signal from the cube is detected. Once it is detected, a goal will be plotted depending on which IR receiver on the rover picked up the signal. For example, if the east receiver on the rover picked up the signal, the mapping task would first find the rover on the map and then plot a goal to the right of it. The navigation task will then drive the rover to the goal, and if the goal was set by an IR receiver, it will continue sweeping until an obstacle is encountered. Upon finding an obstacle, the ultrasonic sensor will measure the width of the object. The IR LEDs, in tandem with the measurement provided by the ultrasonic sensor, will confirm whether or not an obstacle is a cube. That's it. Okay, so for our navigation task, this is an example map so I can show you how the algorithm works. It's a simple 4x4 map with the rover here and the goal there. And basically, the algorithm goes by traversing every cell in the map and making decisions based on the boundary cells. So for example, if it starts here, it's going to look here and here. First, you see that there's a goal in the boundary cell, so it's going to fill this with a 1. Then it goes here, and look up all its boundary cells, and then if there's no goal and if there's no rover, it'll look for the minimum number and add a 1 to it. So for example, the empty, 1, so it puts a 2 here because it adds 1 to the 1. It'll continue doing that, so for here it'll do 3, then 4, then it'll go up here, see that's the goal, so it'll skip it, go here, see the goal is the boundary cell, so it'll put a 1, then it'll go here, look at the next minimum number in the boundary cells, it'll see the 1, put a 2 here, and put a 3 here. Then it'll go here, start the same thing, it'll see the goal next to it, put a 1, then a 2, then a 3, because it adds the 1 to the 2, and then it'll go here, see there's a rover. Now it's counted a rover and look at its boundary cells and see if there's any numbers. So it'll look here, see there's a 3, and then calculate the best available path from there. So it'll go 3, 2, 1, and the path is straight up. Or it could go here, depending on which cell you look at first. So it doesn't matter because both paths are the same and lead to the same goal. And then I can also show you how it works with obstacles. So for example, if the rover does its first sweep, sees an obstacle here, it'll fill it out there, and the map will be passed then down to the navigation task, and then it'll start the process over, beginning at the top cell. 1, 2, 3, 4, 1, 2, 3, 1, 2. It'll see obstacle and skip it. Then it'll go here and see that it's a rover. So then it'll look at its boundary cells and look for a number. And if it sees a number, which it does, 3, it'll see the best available path, which will be the same path as before. But it won't see this path because of the obstacle. That's basically it.
Any user can operate the rover with the web server interface. The web server runs off the ARM board and is accessed through a computer connected to the ARM via Ethernet. Each objective can be selected using the radio buttons, and the values are entered in the text fields. When those values are committed, the web server code parses the URL string to find the appropriate values and sends those values to the main ARM code.
According to our paper written at the beginning of the semester, we proposed that we would accomplish all of the objectives, including the optional objective. We were able to complete objectives 1 through 4 successfully through the assembly of our rover. The selected sensors and emitters, as well as accurate motor and encoder calibration. Specifically, the ultrasonic sensor implementation was successful since it met the obstacle avoidance requirement. The IR emitters and receivers were successful since they provided the necessary data for cube direct detection. In terms of guiding the rover, the mapping and navigation tasks on the ARM were able to determine the best paths for each objective. The optional requirement of real-time mapping was unable to be integrated with the final ARM code due to possible memory issues, but the API was set up. Occasionally, the sensor data received from the ultrasonic sensor was inaccurate, but this was compensated for in the mapping task. The rover moves slowly since it waits for an ultrasonic sweep before driving the motors. Sometimes the rover would wait for several sweeps before moving. Although this increased the amount of time the rover had to operate, it also showcased the reliability and robustness of our rover, since it had to operate for long periods of time in order to complete tasks. One of the design requirements we needed to change was the way we were implementing the ultrasonic sensor. Originally, we were going to have 4 ultrasonic sensors with 1 point in each of the cardinal directions. We decided to change this to a servo-mounted ultrasonic sensor as it was more versatile and provides more useful data, especially when attempting to find the cube.